I'm from South Louisiana. Any family here? No way.
Three-part series beginning today. Guests from Eastman Chemical. Today we'll be talking about the chemistry of things going on at Eastman Chemical right across the interstate from us today. Next week we'll talk about the chemical engineering. The chemical engineers work for the chemists, pushing things around. And then next week also we'll have a bus tour in the afternoon from about 1:15 to 2:50 or so, in between lunch and before lab time. So if you're interested in the bus tour, which will be taking place next week after lunch on Thursday, we need to get your name. So I have a little sign-up sheet here, okay? And there's a certain number of people who sit on the bus, and we cannot hold more than that. And we need to know your name for security purposes, and it's very helpful if your last name comes first. And then also it would be good to have your email address in case we need to contact you with respect to any information regarding the bus tour. You have to wear closed-toed shoes, long pants, stuff like that. Yes? Yeah, we'll be leaving about 1:15, be back by 2:50. So after lunch and before lab, we should be able to do all your lab by then. So I'm going to pass this around. If you want to come on the bus tour next week, make sure you get your name and your email address on here. And this is a commitment that you're coming. Because if you sign up and somebody else wants to come, but you signed up and you don't show up, you're preventing somebody else from getting on the tour. So, turn this around. Okay, sign up for that if you want to be a part of that tour. And I was talking to our speaker here before the seminar, and he tells me that you guys will have a better tour of what goes on at Eastman Chemical than even families of Eastman employees. Yes? Because Eastman employees aren't even, their families aren't even allowed to enter the gates. So you will get past the gates and see more than the family does of Eastman employees. Okay? All right, so let's introduce our guest today, our guest speaker. Damon R. Billodeaux. Did I say that right?
You did.
Billodeaux. Okay, we're practicing. Okay. And he's a PhD chemist. He's been at Eastman for 10 years or so. So he knows what's going on. And he's in the sort of specialty product type thing, where they start making new things and try to sell these new things, in addition to selling their old, regular cash crop type of stuff. So let's give him our attention. And I'm going to
thank you for the invitation to come out and talk this afternoon. I'll try to work through this mouse thing here. So a little bit about Eastman. We are a global specialty chemical company. Our headquarters is in Kingsport, Tennessee, which is extreme northeastern Tennessee. It's pretty close to the Virginia border, actually. We have approximately 15,000 employees and 50 manufacturing sites. We've won a number of awards, such as Energy Star Partner, Responsible Care Company. 2015, our global revenue was about $9.6 billion, which puts us somewhere in the upper 10 of chemical companies. BASF, Dow, ExxonMobil, they're the top, and we're in the top 10. Well, I'll come to that. The Longview site is actually our second biggest manufacturing site. So the Kingsport site is the largest. The Longview site is the second largest. So a little bit of, thought I'd do an introduction of myself. My BS in chemistry is from LSU, which is the single greatest place in the world to watch a football game. I graduated in 2000, so I can now say right about the turn of the century, which makes me feel kind of old. My PhD is in inorganic chemistry at Texas A&M. I have a little further there. So I've been flipping back and forth between Louisiana and Texas most of my life. After I graduated in 2005 from A&M, I took a postdoctoral fellowship, which is a common thing to do after you get a PhD. You go to yet another university and spend a couple more years doing research. I went to the School of Dentistry in New Orleans, so I was a dentist for a year. I worked in a lab that was working on filling materials for teeth, so a lot of chemistry goes into medical devices, medical applications. So I just like to point that out to show the diversity of things that you can do with a chemistry degree. So I worked on filling materials for about 6 months. That was February of 2005 until about August. A hurricane rolled through New Orleans, flooded the building, and I started looking for a new job. And that was how I wound up in Longview at Eastman. I have been a principal chemist at Eastman since 2006. In 2014, I took a career detour. We began a research partnership with North Carolina State University in Raleigh. We have a small office on campus, and it's actually staffed with Eastman people. And I was one of the people that was asked to go to Raleigh. And I spent 2 years in Raleigh doing university relations. And so I think that's why David asked me to come give a talk today, because it's not the first time I've spoken to a group of undergraduate students. So I was there until the end of 2015, and at the beginning of 2016 I came back to Longview, and here I am now. So here's a map showing our various manufacturing locations. The star right here is Kingsport, and here's Longview right there. And then we have a site in Texas City, which is just outside of Houston, going towards Galveston, right on the coast. And then you can see we have a number of sites throughout mostly the eastern half. We do have a site out in Canoga Park, California, which is outside of Los Angeles, where we make electronic films. These are films that we lay down metal electrodes on top of, and they're used to make blood sugar testing devices for diabetic patients. It's pretty interesting. Then we have a number of sites in Europe and Asia, of course. And so Eastman's grown from this 1-2 site company in the 50s into this global manufacturing company today. So chemistry. Almost all the chemistry that we do at Eastman at one time started in somebody's lab in a round bottom that looked, probably similar to that, with a reflux condenser and an air tube. And it takes a lot of study and a lot of fundamental knowledge to go from there to this, which is what we call a bench unit or a mini plant. And so you can do it in a round bottom, but if you can't do it in a continuous process that makes thousands or hundreds of thousands of pounds of product a year, it doesn't do any good. So you have to have a lot of skill in scale up and understanding the reaction mechanisms and the reaction kinetics in order to do that. And then you get together with the engineers and you go from there to this, which is a world-scale production facility. And then to this, which is an overview of the Texas site. So you have not just one unit op, but hundreds of unit ops making all kinds of products around the clock, 365 days a year. Things that we're interested in from a chemistry standpoint: solids, their crystallization processes. Crystallization is a common separation technique. gases, the kinetic theory of gases, intermolecular forces between liquids, such as their vapor pressure, their boiling point, their flash points, their kinetics. How do we distill them? When a reaction is carried out in a giant reactor, the liquid that comes out of that is not usually pure product. There's usually byproducts, there's unreacted starting materials, maybe you run it in a solvent, so you have to do one or more distillation ops in order to recover, purify, and separate the impurities. We care a lot about principles of reactivity, such as entropy, free energy, acids and bases, how they react. Equilibrium is often very important. Phase changes, chemical kinetics. If you can make a 0.1% increase in the rate, that means 0.1% more output, and 0.1% over a billion pounds is a lot of material and can translate into a lot of money. So we're constantly studying our processes and improving them. Finding new catalysts, cheaper catalysts, finding ways to start with cheaper starting materials, fewer starting materials, those sorts of things. And all of this is chemistry. So I thought I'd talk about one particular reaction a little bit more in depth, and that is the hydroformylation reaction. The hydroformylation reaction is pretty much the backbone of what we do here in Longview. It involves taking propylene, which is a C3 olefin. So anytime you have a double bond in the hydrocarbon, we refer to as an olefin. Take the olefin and react it with hydrogen and carbon monoxide. And that combination is called syngas. It's short for synthesis gas because you can use hydrogen and CO to synthesize a lot of compounds. We call it syngas. Combine all of that with a catalyst, and you will get a C4 aldehyde coming out, butyraldehyde. The reaction gives two isomers, the linear isomer, which we call the normal isomer, and the branched isomer, which we call the iso. And so for the rest of the talk, you'll hear me refer to the N to I ratio, and that's what we're talking about, the amount of the straight chain molecule versus the amount of the branched molecule. And those products are used to make different materials that we sell. And so understanding that ratio can be pretty important what we're doing. The hydroformylation reaction has been around since the 30s when it was discovered by a guy named Otto Rowland. And he used a cobalt catalyst, specifically this dicobalt octocarbonyl. The reaction ran at very high pressure, 3,000 to 4,000 pounds per square inch. And it gives lower selectivity to the products because when you've got that much hydrogen around, you get competition between doing the hydroformylation and just adding hydrogen across this double bond, which gets you back to the starting alkane, which isn't useful for anything except putting in a cylinder and having a crawfish. Cobalt's pretty cheap, so people began scaling up this process because you can do a lot with aldehydes. Aldehydes are very reactive. Beginning in the 1970s, different groups, especially Jeffrey Wilkinson at Harvard University, began experimenting with rhodium. And they found that with rhodium, you could switch to a low pressure operation. So it's a lot cheaper to have gas at 100 to 200 pounds per square inch than it is to have it at 2,000 to 3,000. Because it takes a lot of electricity to run gas compressors to boost your pressure up that high. And your reactors have to have a lot more expensive metallurgy in order to hold all that pressure in without bursting. Also gave you more options on selectivity towards your normal or iso products. So here is kind of a big block diagram, we like to say, of Texas operations. And here is the oxoaldehyde section. For whatever reason, it's not entirely clear to me. In industry, they refer to hydroformylation as the oxo reaction. There's no oxygen involved, so I don't know why. You do add an oxygen to the olefin. Engineers get really creative when they start naming things. They don't necessarily follow chemical norms. So, we add oxygen, so it's the oxo reaction. There's ethylene, and we add chlorine, so it's ethylene chloride. well, no, it's dichloroethane, but hey, that's okay. So from the aldehyde block, we flow down to a number of other blocks, and so the aldehyde material is extremely important to a number of derivatives. From the butyraldehyde section, we make any number of materials. From butyraldehyde directly, we actually make windshields. So in Indian Orchard, Massachusetts, we have a plant where they take butyraldehyde and they react it with a compound called polyvinyl alcohol. They make a material called polyvinyl butyral. And that plastic is actually quite sticky. And they take that and they stick it in between two panes of glass. And then they do what's called a lamination process, which causes those two panes of glass to stick together. And that's what makes your windshield. And the reason why you have that plastic insert is so that when a rock hits your windshield, your glass doesn't shatter, it kind of spiders. Okay? It's also got architectural uses as safety glass. They have the coolest lab up there. They have a lab that all they do is break glass all day. So they'll take a windshield, they'll drop a steel ball from 5 feet into the windshield, and they'll say, okay, did it go all the way through? Great. And they'll take it up higher. They have another one where they actually shoot 2x4s at glass, and that simulates hurricanes or tornadoes, and that's their safety glass for architectural applications. And then my favorite is the one where they take airplane windshields and they shoot frozen chickens in it to simulate bird strikes. The butyraldehyde also goes into plasticizers. That's probably the biggest volume material. Your PVC, toys, various other plastics are really, really hard. And so to make them soft and malleable, they'll put a plasticizer in them. Many of those plasticizers start with butyraldehyde. You take the butyraldehyde, you add oxygen, hydrogen, you'll get butanol. That goes into cleaning solvents, inks. If you add oxygen, you get butyric acid, which by itself is a quite smelly compound. But when you make salts of it, it goes into food preservatives, it goes into animal nutrition. You can also take the butanol and the butyric acid and combine them with other compounds, and you can get esters that go into different fragrances. A lot of perfumes have a number of esters, and also flavorings. Artificial grape, banana, apple, those are all ester compounds. On the iso side, isobutyraldehyde goes into paint additives. So one of the things that we're well known for is a compound called Texanol. Starts with isobutyraldehyde. We've been making it for over 50 years. And it's a coalescent in paint. So when you spread, your paint is a bunch of solid, little bitty solid particles mixed with different solvents and different other additives. When you spread it on the wall, the Texanol helps give you a fine film and keeps it from clumping and then evaporates off. And that's what they call it, a coalescent. Isobutanol goes into different coatings and paint solvents as well. The isobutyric acid can also be used for food preservatives, and it is one of the key monomers in our Triton polymer, which is our BPA-free plastic that goes into reusable water bottles and household items, baby bottles, any number of things. That's been one of our more recent smashing successes is the Triton monomer. That process was developed and piloted in Texas at Longview before it was commercialized in Tennessee. So billions of pounds of Eastman products per year are based on Texas aldehydes, and that's why aldehydes are important. So I talked a lot about this N/I ratio. So what controls that? Well, the biggest thing is phosphorus is ligands. So ligands are any molecule that you stick on a metal. So the picture I've got down here, it could be that hydrogen, it could be the carbon monoxide, and then the L is this phosphorus. And the neat thing about phosphorus is it has a very versatile chemistry, so you can do a lot of things with it. You can add a lot of other organic components to the phosphorus, and so there's thousands and thousands of different ligand combinations you can come up with. And they all play a role in controlling what the metal does in hydroformylation. So if I start over here and I get just one phosphorus on, I'll get higher activity and a lower end-to-eye ratio, but it's less stable. So if I dump a bunch of additional phosphorus into my reactor, I can push it toward what they call the bis-ligated species. So you've got 2 phosphorus on there. And that gives me lower activity, but it gives me greater stability, so I don't have to replenish my catalyst as often. So you have to do this balancing act with the equilibrium between how much mono you want in there and how much bis, so you can control the end-to-eye ratio, control the catalyst stability, and control how much propylene you're chewing up over time. That's the activity portion. So a number of these catalysts have been commercialized by different companies. They've all got their own proprietary spin on it. Triphenylphosphine was among the first. Then they came out with this sulfonated triphenylphosphine. The neat thing about that is that it's water soluble. So you can run the reaction in a mixture of water and organic, and then when you get to the end of the reaction, your product, which is an organic, stays in one phase. Your ligand, your catalyst, stays in the water, and you can, water and the organic don't mix, so you can decant the water, send it back to the reactor, and make your catalyst and product separation a lot easier. Eastman has its own proprietary trialkylphosphine ligands, and that's what I'll talk a little bit about today. So, Eastman's dilemma. The majority of the industry wants that normal isomer. Okay, they don't care about the iso; they burn it, or they make isobutanol and sell that cheap. Eastman came up with this idea that they were going to make their own niche from the iso derivative. Everybody else was selling normal. We're going to make some things off of iso. That's how they came up with Texanol. That's how they came up with a molecule called neopentaglycol, which goes into fiberglass coatings for boats and other things. And so the challenge has always been to make the right amount of the end-to-eye ratio that the business needs at any time. And so our catalysts are actually developed to give us more ISO than what the rest of the industry typically does. So we've been basic in oxide technology for a long time. We have an R&D program to support the derivatives. We actually have a state-of-the-art pilot plant and semi-works that allows us to take the catalysts that we develop in the lab and scale them up before they'll be commercialized. And talked a little bit about the bench unit earlier. So the trick is to be able to come up with a catalyst that will allow us to actually use like a dial to dial in what ratio the business needs at any given time, depending on if butanol is selling more or the isobutanol. So our approach has been, for 30 years, make new ligands. We stick them in an autoclave, which is a little metal reactor, test it out, see how it does. If it looks good, then we go to our bench unit, run it for 8-9 hours a day to see if we get that stability that I talked about, if it doesn't break down, to see what its activity is actually over an extended period of time, and then from there to scale up. Over the years, Eastman scientists have tested more than 400 ligands. Okay? I told you that phosphorus chemistry is very, very versatile. You can do a lot of things with it. I do it all the time. So Eastman started with the cobalt technology like everybody else. They wanted to switch to low-pressure rhodium technology. Dow and a number of other companies had already patented the triphenylphosphine and other ligands, so we couldn't use that. So we started developing our own particular ligand. So the way it works is you set up a team and you make ligands and you repeat the cycle. So what we did was look at a number of ligands that had this structure where you actually had 2 phosphoruses on there, right? I talked about that monoligated versus bis-ligated. Well, if you can make one ligand that had 2 phosphorus, you can get that bis-ligated species with just one molecule, which would save you money in the long run. And so over a number of years of different synthetic techniques and testing and retesting and going back to the drawing board, came up with this molecule called Bisbee. Turned out that Bisbee had an end-to-eye ratio of 25, which was better than the best commercial catalyst at the time, which was 10. But like I said earlier, Eastman was more interested in a catalyst that would do lower into high ratios. And so we had this super high ratio catalyst, and we decided to use that as a licensing opportunity. So we licensed that out to other companies that are more interested in the normal products than we are. Occasionally, when business conditions call for a lot of normal butyraldehyde, they'll put Bisbee back in a reactor. But it's not typically used. So, organic chemistry, very important. The purpose of this slide is to show that there's a number of routes that you can follow to get to the same product. And what's important about that is just because I can do this route, for instance, in my 100 milliliter round bottom flask in my lab, that doesn't mean I can do it in a 1,000 liter reactor on the commercial scale to make the amount of lignin I need to run a 1 billion pound per year plant. This starting material may be really expensive, where this starting material may be really cheap. So it's important, if at all possible, to have a number of different reaction pathways to get the same product so that you can find the one that makes the most economic sense. Some things there may only be one pathway, at which point your financial people, your engineers, your chemists have to get together and say, okay, is the end product and what I can sell it for worth the amount of money it's going to take me to make this liquid? Sometimes the answer is yes, sometimes the answer is no. Sometimes the answer is it depends on the year. Okay. I talked about the fact it's a high ratio catalyst. It's been operated commercially for almost 20 years by different companies that we've licensed it to that are more interested in butanol than we are. And you can actually Google Bisbee and get about 3,000 hits. It's got a lot of academic studies that have been done with it too by different groups that have studied hydroformylation mechanics and mechanisms and kinetics. All right, halophosphites. So those are compounds like this, where you've got these oxides coming off phosphorus along with a halogen. And what happened here was one of our chemists was reading a paper, and they claimed that this molecule that they were selling as an antioxidant was stable in air and stable in, what did he say, various, yeah, stable in water, stable in air, and stable under various reactions. He didn't believe that it would work, but he said, okay, this looks like, you know, it's a tried organic phosphorus. Maybe it'll be a good ligand for hydroformylation. But it couldn't possibly work, because there's two things you always worry about with hydroformylation. One is sulfur, and one is a halogen. Both of those things will poison your rhodium and shut down the reaction. If the catalyst that has this halogen in it, fluoride, chloride, iodine, breaks down during the reaction and gives you free fluorine or free chlorine, then it's going to poison your catalyst and shut down the reaction. But gave it a try. So he made a number of fluorophosphite ligands and threw them in the reactor, and lo and behold, he started making olefin. Also looked at the chlorophosphites. So the surprising thing was that this particular compound here, with all these chlorines on it, was actually stable under hydroformylation conditions. It turns out that the phosphorus fluorine and the phosphorus chlorine bond, when you put enough organic flora around it, are quite stable. Normally with PCl3 is extremely reactive, the chlorine comes off quite well. But when you start putting these aromatic rings with all these electron withdrawing groups on them, it actually pulls enough electron density away that the phosphorus starts drawing it from the chlorine bond and helps stabilize the catalyst over time. What became even more surprising was that they could take this ligand, put it in a reactor, and if they adjusted the hydrogen to carbon monoxide ratio in their syngas mix, they actually got a flexible end-to-eye ratio. So it started out as something that they were looking for a lower end-to-eye ratio, and turned out that they could go from 4 to nearly 8 on their ratio just by adjusting the CO pressure within the reactor. And that's an easy dial for an engineer to turn on this plant. It also gave pretty good activity over the lifetime of the catalyst. So lo and behold, we now had a flexible end-to-eye ratio catalyst. You didn't have to worry about, okay, do I use catalyst A because the ISO is selling so well right now, and then switch to B later. I can use the same catalyst in my reactor and just change the CO pressure and get the ratio that I want. You can also make ethylene, you can do hydroformylation with ethylene. It gets you to propionaldehyde, which is the C3 aldehyde. When your ethylene comes out of your crackers, you can sometimes get acetylene, which is a byproduct, and it's a poison. And so what I want to show over these slides is that you often have to worry about not only your starting material, but what's coming in with your starting material, because poisons can have a dramatic effect on your reactor. So they were looking for acetylene-tolerant catalysts because they wanted to use lower-grade feed materials at the cracking plants, which would produce lower-grade ethylene for the aldehyde plants. And you can see just adding 1,000 parts per million acetylene to the reactor has a dramatic effect on these other 3 catalysts that are commercially available. But their experimental catalyst was remarkably tolerant to the acetylene. It's also recoverable, so if you really flood it with acetylene, 10,000 parts per million, and your catalyst activity drops off, if you dump more catalyst in, well, then it recovers. But tolerant is better than, okay, I've got to dump a lot more catalyst in there in order to get my activity back up. So the lessons that were learned from this particular study is that the acetylene impact is related to the electron density at the phosphorus atom. So all the things you put around the phosphorus molecule, you can have electron donating, you can have electron withdrawing groups, and so the more electron density that you add into the ligand, the better, the more tolerant it is to the acetylene impact. Concentration of acetylene is important. It was tolerant at 1,000 parts per million. At 10,000 parts per million, it collapsed, crashed. But while the poisoning was severe, you saw how far the activity dropped. It's also recoverable. But you would prefer not to have to recover because it costs money to put more rhodium and to put more ligand in. Rhodium is an interesting metal. It's one of the 3 things that goes into your catalytic converter in your cars. So when car sales are doing well, rhodium price is high, and that's bad for us when we have to buy more rhodium to put in the reactors. So it fluctuates pretty well with car sales. When I started in 06, rhodium was selling for something like $14,000 per troy ounce, which is astronomical. And then in 2008, it crashed to like 2,000, so we were saving all this money on rhodium at the time. And now it's come back up to around 7,000, which is a little bit more manageable than 14,000. We actually have extensive programs in things like metal recovery, particularly for rhodium, because eventually the catalyst does die. It lasts for a while. You've got to put more rhodium in. You get this sludge out of the bottom of your reactor that's full of rhodium, and so any of that we can recover and reprocess saves us money in the long run. So we started out with the cobalt technology that everybody else was running. We moved into some proprietary trialkyl phosphine ligands that were similar to what other companies were running, but not the same thing. The halo phosphite was a Hail Mary long shot that turned out to pay off, and we've been running a commercialized version of these halo phosphite catalysts since 2002. to allow us to dial in the N-to-I ratio at any given time. We actually have 5 lines, what they call lines, 5 different reactors doing this hydroformylation chemistry. 4 of them make the butyraldehydes and 1 makes the propionaldehydes. So depending on business conditions at the time, and they tend to project these things out several quarters in advance, you can run different combinations of catalysts in those reactors to make the N-to-I ratio that you want. So we may have the flex ratio catalyst in 2 reactors, and then Bisbee in 1 to make a lot of normal, and then something else in 1 to make the propionaldehyde. So there's a lot of planning that goes into which catalyst and how are you going to balance the product mix coming out. Thought I'd talk a little bit about chemistry careers at Eastman. There are a number of different disciplines that you can go into. As a chemist, if you have a bachelor's degree in chemistry, we hire a number of talented people with those degrees to be our laboratory technicians. And those are the people that work with me. They're usually my hands in the lab. So when I'm at LeTourneau giving a seminar, I have a technician back in the lab running the experiments that I gave her that morning. You can do chemistry and chemical engineering. Polymer science is very important. We make a number of specialty polymers, both in Longview and in Kingsport. We don't make the commodity polymers anymore, the polyethylene, the polypropylene. But we have these specialty polymers here that we call APOs. In Kingsport, we have a number of specialty polyesters like Triton, other things that we make. Polyvinyl butyral that goes in the windshields is a specialty polymer. Material science is very important, so you can get a degree as a material scientist, studying polymers, studying textiles, textile chemistry and engineering are all very important. We employ a number of mechanical engineers. We have pumps, we have giant mixers, those sorts of things. All need maintenance and picking the right pump and the right mixer for the right process. Statistics are actually very important. We have statisticians that have math and chemistry degrees on staff that help plan experiments with PhDs and help understand the data. As a PhD, I was taught, okay, do one experiment, then we change one thing, one variable at a time, and that may take you several months to run a series of experiments to understand all the interactions that are going on. Statisticians actually have software and modeling techniques where you can change 3 things at once, run fewer experiments, and then you can get the statistical interaction of the different variables. So you can actually see how time, temperature, and pressure affect your conversion at the same time, for instance. Biological sciences are becoming more and more important as people become more and more interested in bio-based starting materials. Aerospace engineering, we wouldn't have thought Eastman would be in aerospace engineering at the time, but as we sell materials into automotives, into aeronautics, lightweighting materials, things that aren't traditional metal alloys, we can make those things. Understanding those become more and more important. So a number of different things. You can go to our website for more information on what's currently available, what we're currently looking for. So I'd like to thank all these people that did most of the work that I've talked about. A lot of these ligand development was done before I got there. And if there are any questions, I'll be happy to answer.
Plenty of time for questions. One question might be, why butyraldehyde? Why don't you call it butanal, like everybody else does?
Yeah, so if you type that into ChemDraw, it will pop out butanal. And if you look in your organic chemistry textbook, it says butanal, propanal. I don't know where butyraldehyde came from.
Old lingo.
Maybe it may be old German lingo before the what do they call it? The IUPAC standardized all the naming nomenclature.
Okay. Question up front.
You didn't mention anything about a connection to Kodak.
No,
And was that intentional, or do you not like to talk about it?
not really. So, because so Eastman Chemical was founded by George Eastman in the 1920s as the chemical arm of Kodak. And the story is that during World War I, all the chemical industry was in Germany. And so during World War I, he couldn't get chemicals that he needed for his photography business. So after the end of the war, he swore that would never happen again. So he started looking for sites to build a chemical plant. And he came upon this old wood plant in northeast Tennessee. So they used to take wood, and you could do what they call wood pyrolysis, where you heat it up really, really hot, and you could get methanol to come out of the wood. And methanol was a very important chemical in the photography business, probably still is an important chemical in the photography business. So he bought this wood alcohol plant and turned it into a chemical plant to make photographic chemicals. In the 50s, when oil was booming in northeast Texas, they said, okay, we're going to build a chemical plant down in Texas where we can get oil cheap and make chemicals off of that, and that's how the Longview site was developed. In the mid-90s, I guess, the Kodak company decided they were going to get out of the chemical business, and so they divested of, spun us off as an independent company, and so that's our linkage to Kodak. But for a number of years, we were part of the Kodak company. And since we spun off, their stock did this and our stock did that. The story of the rise and fall of Kodak is pretty fascinating. Kodak, they had the digital camera. Kodak had a patent, or they had technology in the 70s for a digital camera, but there were two things. One, it was a box, so it was about that big, and it had a huge storage device. And they just didn't anticipate how fast technology would move towards developing memory that you could store thousands of pictures on. And they had a booming film business. Kodachrome film was the gold standard for film. And they thought, if we develop this, we're going to cannibalize our film business. So they just stuck it on a shelf and forgot about it. The rest, I guess, is history. But I didn't intentionally leave out Kodak. I was never a Kodak employee. I got here in 2006, so it was already been spun off for a number of years by the time I got here.
But Kodak still owns Kodachrome, right?
Yeah.
That's why we can't get it anymore.
As far as I know, they still own it. I can't remember the last time I bought a roll of film.
The questions from the audience?
Are these processes, like, do you just pretty much mix in fixed ratios and something happens, or are you kind of constantly dynamically tweaking them with control systems?
They're constantly dynamically tweaking them. Yeah, especially the CO, partial pressure, in order to get that end-to-eye ratio to be what they want. And this is a thing where you flip on a switch, and the propylene starts coming in, the CO comes in, the hydrogen comes in, and you're constantly taking the product out the back and sending it on to distillation. And each of these plants probably runs 300 to 325 days a year. There's plant shutdowns in there for maintenance and cleaning things out. In order to run billions of pounds. And then they have a computerized control system, so they can change when they need to how much is going in.
About how many control variables are there?
You can change temperature, you can change pressure, you can change the feed ratios, you can change the amount of ligand that's going in, 4 to 5, and it's different for every unit.
Well, nobody dares to ask, but let me ask for them, because they've all been asking me. What is that flare? Like, what are we telling our students?
Eye of Sauron?
We have a number of flares, actually. That just happens to be the biggest one. Usually when there's so we bring in, we'll go back to, David's going to talk about this next week, but I'll jump ahead of him. So we bring in ethane and propane, and they either come in, well, so that we get most of that from oil or from gas production. So that comes in and it goes into what we call our crackers. And the cracker is really a gigantic furnace that heats up to 700, 750 degrees. And the ethane and propane go in, and you thermally crack the molecule, which means you get hydrogen off of it to produce the olefins, the propylene and the ethylene, and the hydrogen that you use for other processes. Okay? So when the crackers, when there's an upset in the crackers and they have to shut one of them down, they can't just turn off the ethylene gas coming out of the cracker. Well, usually the problem is the problem in one of the plants, the downstream plants. And when that happens, they can't just turn the cracker off. The cracker has to keep running. And so if the ethylene or the propylene can't go where it usually needs to go in order to become some product, they send it to that giant flare to just burn it. If you shut down a cracker, unless there's an emergency, you can damage the internals. You also sometimes can't shut down the ethane that's coming in for whatever purpose. It's all about logistics and balancing where material is, where it's going, and where it's ending up. So sometimes it's easier and safer to just send it to the flare and burn it rather than try to shut something down. So that's usually what that flare. If there's a major upset at the plant, a major safety, then everything dumps to that flare. And if it ever becomes a towering column of fire, you'll know there's a serious problem. Usually there's a planned shutdown of, like right now we're having an OXO turnaround, so the OXO reactors are actually not running. The crackers can't be shut down because we still need the ethylene, so the propylene may be getting sent to the flare to be burned during the shutdown.
So they're burning up their product.
Starting.
So you want that flare to be off.
Yeah.
Most of the time.
Yeah. Usually those shutdowns are planned for, so they know in the budget that that amount of propylene is going to be burned during that period of time.
Okay. Otherwise, we will have another Eastman chemical talk next week. Okay. They go yet. Go down.
Where's the physics signing?
Where's the chemistry?
Hang on.
Chemistry signing.
Turn around. Settle down. Okay, there we go. All right. So next week we will have a chemical engineer speaking to us, and we'll have a bus tour. Hopefully the sign-up sheets for the bus tour went around, and hopefully other sign-up sheets went around as well. So all come down here to the front. Okay. So if you need to sign up for something, you can sign up. At the hour. Okay. Let's thank our speaker one more time. See you next week. Welcome to join us for lunch too at Joyce Room.